The window regulator is connected to the window motor. As the window motor turns, it rotates a large pulley that pulls a cable guided by other pulleys. Window clips attach the window glass to the cable, and as the cable moves, the window is raised and lowered. Reversing the polarity on the window motor changes the direction that the motor turns. Typical failures of the window regulator include broken clips, pulleys, and cables. Broken clips cause the window to become wedged in an angled position inside the door. Broken pulleys cause the cable to become bound, and the window becomes stuck in place. Broken cables cause the window to drop down into the door. Another common failure of the power window motor is an overheated motor. Motors can overheat due to internal problems and will not have the power sufficient to raise or sometimes lower the window. As soon as the window motor cools down, the window will raise and lower again for a time until the motor overheats again. Sometimes a window may only travel a very short distance until the window motor overheats. In some vehicles, the motor and regulator can be replaced independently. However, in most cases, the motor and regulator are replaced only as a complete assembly. The ribbon cable inside a clock spring has multiple copper tracks, allowing the various steering wheel mounted buttons and the airbag to be connected to the wiring harness. When the clock spring is installed, it is normally preset to a middle position that allows the steering wheel to rotate through its full range in both directions, without making the coils of the ribbon cable too tight. A break in one of the copper tracks of the clock spring ribbon cable will cause the failure of one or more steering wheel buttons, or the airbag circuit. If the airbag circuit fails, the warning light on the instrument panel will illuminate. Many vehicles use seatbelt pretensioners to reduce injuries in an accident. The pretensioner is usually an explosive charge designed to retract the seatbelt when a crash is detected by the collision impact sensors. When a collision is detected, an explosive charge is detonated, which shoots ball bearings out of a tube. As the bearings move past the seatbelt reel, the reel is turned, causing the seatbelt to be retracted and the occupant to be pulled back into their seat. This lessens the effects of whiplash and the potential of injury from the inflating airbag. After a pretensioner has detonated, the seatbelt normally becomes jammed. An exploded pretensioner must always be replaced. The contacts inside the seatbelt latch are usually made up of a copper strip on a small printed circuit board. Releasing the buckle turns the seatbelt light on. Inserting the buckle opens the circuit and turns the light off. Some latches contain two switches. One switch operates the light, and the other sends a signal to the airbag module as to whether the seatbelt is being used. Many vehicles now use seat occupancy sensors that detect whether the seat is occupied and the approximate weight of the occupant. This information is used to determine whether, or in some cases how quickly, to inflate the airbag and activate seatbelt pretensioners. Worn wiper blades are usually caused by exposure to sunlight and extreme temperature changes. Blades can fail in many ways, but the most common type of failure is deformation of the wiper blade. This occurs when the wiper blade becomes hardened and retains the curved shape that it takes when the wipers are parked. A wiper in this condition is not able to clean a windshield properly and often skips or chatters across the windshield.
Vehicle headlamps have improved significantly over the years, improving road visibility and safety. The latest technology in headlight systems use LED lights, which are brighter and more efficient than halogen or high-intensity discharge xenon bulbs. Even when your headlight bulbs are functioning correctly, the amount of light hitting the road can be significantly reduced due to oxidization or discoloration of the headlamp lenses. Fortunately, it's possible to restore the performance of your car headlamps without replacing the lens. Your technician will mask the body panels around the headlamp to avoid any accidental damage to the paint. Use specialized abrasives to remove the oxidized surface on the headlight lens. And then polish the light to restore a clear finish that allows the light from the bulbs to shine through clearly. With restored headlamp lenses, your nighttime view of the road will be much clearer, and your vehicle's appearance will also be refreshed.
Cracked windshields are more susceptible to breakage, provide less support to the airbag in the event of an accident, and reduce visibility. Unrepaired chips can develop into a crack at any time, but especially when the temperature is very hot or cold, resulting in the need to replace the windshield. The chip can be repaired if the following conditions are met. If the chip is in the driver's line of sight, the diameter must not exceed ½ inch. In other parts of the windshield, the chip diameter must not exceed 1 inch. The chip must be more than 2 inches from the edge of the glass. The chipped area is prepared by using a cleaning solution, then a special drill to remove loose glass and allow the resin into the damaged area. After the area is prepared, a vacuum device is placed over the chip. With the air removed, the chip is filled with a special resin, and the resin is cured or hardened using ultraviolet light. To ensure a smooth surface and to remove any excess resin, the windshield is cleaned and polished. After the resin is cured, the windshield will be as strong as it was before it was chipped. Brake systems generally consist of a vacuum booster to assist the driver in pressing the pedal, a brake master cylinder that pressurizes brake fluid when the pedal is pressed, metal brake lines, rubber brake hoses, disc brake systems, and on some cars a drum brake system. Most vehicles also have an ABS system designed to pulse the brakes on a skidding wheel when maximum braking pressure is applied. In damp climates and areas where salt is used to de-ice roads, the metal brake lines can become rusted. Failure to replace rusted brake lines can result in the line rupturing under pressure, allowing the brake fluid to leak out of the system. When the driver presses the brake pedal, pressurized brake fluid forces the piston inside the disc brake caliper to move outwards. This forces the brake pads to push against the brake rotor. The brake pad has a block of friction material fastened to a metal backing plate. The friction material may be a ceramic, semi-metallic, or organic compound. The friction material wears out after many stops, at which time the brakes need to be serviced. The piston inside the caliper has 2 rubber seals. The outer seal, or dust boot, prevents debris and moisture from entering the caliper. The inner seal, or square-cut seal, traps brake fluid inside the caliper. When the brakes are applied, the square-cut seal twists inside a groove in the caliper and then helps the piston to be retracted when the pedal is released. The drum brake system includes a brake drum, hydraulic wheel cylinder, brake shoes, and return springs. Drum brakes are generally used to stop the rear wheels on older and lower performance vehicles. The drum is connected to either the rear axle or a wheel hub, and the wheel is bolted onto the drum. When the brake pedal is pressed, the pistons in the wheel cylinder move outwards as a result of the brake fluid being pressurized. The brake shoes are forced against the inside surface of the brake drum in order to stop it from turning. This friction causes the lining on the brake shoe to gradually wear out, at which time the brake shoes should be replaced. It is important that when brake shoes are replaced, brake hardware, including the brake return springs, should be checked for rust. Rusty return springs can break, allowing the brake shoes to remain in contact with the brake drum when the brakes are not applied, and causing the brake shoes to wear out prematurely. A common failure of the drum brake system is a leaking wheel cylinder. When the seals around the wheel cylinder pistons start to deteriorate with age, brake fluid can leak past and start to contaminate the brake components. Once brake linings become soaked with brake fluid, they must be replaced. Another failure of the drum brake system is an out-of-round brake drum. This occurs when the drum becomes more oval-shaped than perfectly round and can cause the brake pedal to pulsate under braking. The brake master cylinder assembly is a metal cylinder containing 2 pistons with seals and springs, with a plastic fluid reservoir located on the top of the metal cylinder. The brake master cylinder is usually located at the back of the engine compartment, on the driver's side of the car. When the driver pushes on the brake pedal, a rod from the pedal to the brake master cylinder forces the pistons inside the master cylinder to compress the hydraulic brake fluid. The pressurized fluid, in turn, forces the brakes on each wheel to apply. Leaking seals inside the brake master cylinder can result in the brake pedal moving to the floor when the brakes are applied. A small leak normally makes the brake pedal slowly drift to the floor when sitting at traffic lights with the brakes applied. A major leak will cause the pedal to move to the floor quickly with the brakes failing to apply. When there is a leak somewhere in the brake system, either in a hose, line, caliper, or wheel cylinder, the brake master cylinder is unable to pressurize the brake circuit. This video shows a crack in the metal line exiting the master cylinder. When a leak like this occurs, the brake pedal will often move much further than normal before the remaining functioning circuit is applied. As fluid continues to leak, the fluid level in the reservoir will start to fall, and the problem should be repaired before driving the vehicle any further. Because wheels move in relation to the body of the vehicle as the suspension is compressed or the steering wheel is turned, a flexible brake hose is used to connect the steel brake lines to the calipers on each wheel. The brake hose is made up of three main components: an inner rubber hose, which contains the brake fluid, a steel braid that reinforces the inner hose so that it does not expand under the pressure generated when the brakes are applied, and an outer protective layer which keeps moisture off the steel braid and protects the hose from road debris. When the outer layer cracks, moisture can enter the brake hose, allowing rust to develop on the steel braid. With a weakened steel braid, it is possible for the inner hose to expand like a balloon when the brakes are applied, leading to a potential rupture and the loss of brake fluid, and therefore stopping power. Once a brake line has ruptured, the brake system will not be able to build up sufficient pressure to stop the vehicle. To prevent the risk of brake fluid loss, brake hoses should always be replaced at the first sign of cracking in the outer layer. When the brakes are applied, the brake caliper needs to be able to move freely so that even pressure is applied to both brake pads. This is done by mounting the caliper on slider bolts, smooth bolts coated in grease that can move freely in and out of the brake caliper mounting bracket. These bolts are protected by a rubber boot that keeps the grease in and contaminants out. When the boot is ripped, grease can escape and water can enter, causing the bolt to become seized in place. When only one slider bolt becomes seized, it can cause the brake pads to wear at an angle. When both slider bolts become seized, the caliper is unable to move freely, which puts constant pressure on the outer brake pad, causing it to wear out sooner than the inside pad. If the caliper slider bolts become seized, the brake caliper should be replaced. The vacuum booster shown in this video has been simplified in order to demonstrate its operation. The vacuum booster has two valves, one that seals the booster from outside air, located by the brake pedal, and another that is positioned so that it can seal the rubber diaphragm in the middle of the booster. The vacuum booster assists the driver in applying more force to the braking system. When the brakes are not applied, the valve on the diaphragm is open, allowing vacuum to fill all of the brake booster so no assistance takes place. The valve on the pedal side is closed, sealing the booster so that the engine vacuum is trapped inside. When the brakes are applied, the diaphragm valve closes and the pedal valve opens. In this mode, ambient air pressure fills the pedal side of the diaphragm, but the right side remains under vacuum. The higher pressure in the chamber closest to the pedal pushes the diaphragm away from the brake pedal and assists in the braking effort. The most common failure of the brake vacuum booster is a tear in the rubber diaphragm. When the brakes are applied, air enters the chamber closest to the pedal. However, it also enters the adjacent chamber through the tears, reducing the pressure difference between the two chambers. Since both chambers are equal in pressure, the vacuum booster is unable to assist in braking, and the brake pedal is very difficult to press. Parking brakes can be incorporated into disc brake systems, but the majority of parking brakes utilize the drum brake systems. When the drum brakes are applied by the driver's foot on the brake pedal, hydraulic fluid forces the wheel cylinder to expand and apply the brakes. The parking brake is almost always operated by a cable, not by brake fluid pressure. When the parking brake is applied, a cable pulls a lever which forces the brake shoes to spread apart, pushing them against the inside of the brake drum to stop the vehicle from moving. The park brake also operates the auto adjuster inside the brake drum. The auto adjuster is the bar that goes between the two brake shoes. The star-shaped wheel or gear is attached to a threaded bolt. Each time the park brake is applied and released, an arm tries to turn that star gear to ensure that the brake shoes remain close to the drum, but not touching when the brakes are released.